In this video, we consider the idea of inverse functions for a simple function. Consider this function. We could draw this function as a machine. I feed the function x, and the function spits out 3x minus 1. So, for example, we have 2 turns into 5, and 0 turns into negative 1. We could consider going backwards, and this is the key idea of inverse functions. We have this rule for how to turn 2 into 5 and 0 into negative 1. In particular, our rule is that we take x and we spit out 3x minus 1. But could we write a rule that would turn 5 into 2 and turn negative 1 into 0? In other words, could we write a rule that specifies the associated input to f given a choice of output of f? Well, if we break down f a bit further, this actually becomes quite straightforward. What does f really do in order to turn x into 3x minus 1? Well, in some sense, it first multiplies by 3 and then subtracts 1. It might be a little clearer if I draw this without the box for f and just draw it like this. So by breaking it down like this, I can actually think about how to work backwards quite simply. If I start with some particular number over here, I can simply undo this and then undo this in order to get back to my original number. So in order to go backwards, I could say that if I start with some number, I'll say a, how do I undo subtracting 1? Well, I add 1. And how do I undo multiplying by 3? Well, I divide by 3. And what do I find as my output? Well, I started from a, I added 1 and then divided by 3. I find that my final result here after undoing f is a plus 1 over 3. Let's check that this actually works. If I start with a value of 5 for a, and I run this rule, I get 6 over 3, which is 2. I like that. I started with 5. I ended up with 2. If I start with negative 1 for a, and I run this rule, I do get 0, which matches my association here. So I could say that f inverse turns the input of a into a plus 1 over 3. Now, the letter a here is completely arbitrary. We often write inverse functions still using x. So I could write Now, the key property of inverse functions really is that they undo the original function. In other words, if I start with x, then apply f, and then apply f inverse, I should get back to my original x. Let's check that that works using this f and this f inverse. I have here, I've replaced f of x with 3x minus 1, and now I apply f inverse to this. Just as I had hoped, I have that f inverse of f of x is equal to x. And similarly, I also have the reverse of this being true. If I start with x, first apply f inverse, and then apply f, I should still get back to my original x. So we've seen, given a simple function, how we can compute f inverse. And we've seen the defining property, really, of inverse functions, which is that they cancel out with the original function. In the same sort of sense that addition cancels out with subtraction and multiplication cancels out with division, we have f canceling out with f inverse.